Faraday's law of electrolysis. So class, there are two laws. We first take up first law, which suggests that weight of substance deposited is directly proportional to quantity of electricity passed. Electricity passed. So W directly proportional to Q. So what is Q? Q is your charge in coulomb. But we know from physics Q equals to I into T, where I is your current in ampere and T is time in second. So next step I can write W directly proportional to I into T. Opening the expression, W equal to Z into I into T. So what is Z? Z is called electrochemical equivalent. Okay, let us make equation number 1. If I equals to 1 ampere and T equals to 1 second, then W becomes equal to Z. So class, listen carefully and write in register. How do you define electrochemical equivalent? Electrochemical equivalent is defined as weight of substance deposited during electrolysis when 1 ampere current flows for 1 second. I repeat again, electrochemical equivalent is defined as weight of substance deposited when 1 ampere current flows for 1 second. Now class, let us open the expression. So W equals to ZIT. In case of ZIT, we can write E upon 96,500 multiplied by I multiplied by T. So what is E? E is the equivalent weight of substance. And how do we calculate equivalent weight? Equivalent weight is always, I have already told you in class 11, atomic weight upon valency. So this is the expression for Faraday's first law. Now based on this first law, let's have a numerical here. Find the weight of silver deposited when 2 ampere current flows for 2 hours in AgNO3. Find the weight of silver deposit when 2 ampere current flows for 2 hours in silver nitrate aqueous. Given atomic mass Ag equals to 108. So class, we use this formula. W equals to E upon 96,500 multiplied by I multiplied by T. In class, we know the valency of silver is 1. So in place of equivalent weight, atomic weight upon valency, atomic weight is 108, valency 1, don't write, divided by 96,500 multiplied by I and let us put the value of 5. I is 2 ampere and time is 2 hours, so 2 hours multiplied by 3600. So class, that is going to give me total weight. That comes to 16.11 gram. So this is the way you can solve the numerical. The class during completions, a different type of questions is being asked. So let us move to those questions. But class, before we move to those questions, we must know from where this concept of 96,500 coulomb, that is also called 1 Faraday, I derived from. Class, we know one electron carries 1.6 into 10 to the power minus 19 coulomb charge. Therefore, 1 mole electron will carry 1.6 into 10 to the power minus 19 multiplied by 6.023 into 10 to the power 23 multiply, you get their value 96,500 coulomb, and this is called 1 Faraday. So very important to remember from where this 96,500 coulomb charge appears. 1 mole electron carries 96,500 coulomb charge. Now we are going to take here two questions. Find the charges in coulomb required to reduce a 0.5 mole of copper sulfate aqueous and 0.1 mole of silver nitrate aqueous. Now let us take first one, 0.5 mole of copper sulfate, but before we go to the numerical, just break copper sulfate. Since question is asked, find the charges in coulomb required to reduce. So we all know that copper is going to reduce. How it will be reduced? Copper 2 plus 2 electron gives me copper 0. So 1 mole of copper 2 plus requires 2 mole electrons. 1 mole copper 2 plus requires 2 mole electrons. So in the question given 0.5, so 0.5 mole will require 0.5 into 2, that is 1 mole electrons, and you all know that 1 mole electrons carries 1 Faraday charge, or simply equal to 96,500 coulomb. Let us take the next one. It is silver nitrate. This will dissociate like this, Ag plus and NO3 negative. Write down the reduction reaction of silver plus ion. So this is the reaction. So from this reaction what we get? 1 mole Ag plus requires 1 mole electrons. Here 1 mole copper 2 plus required 2 mole electrons. So we'll simply write 1 mole Ag plus requires 1 mole electrons. Therefore 0.1 mole will require 0.1 mole electrons, and 0.1 mole multiplied by Chandler Ansov will give you 9650 coulomb charge. So class, double click these questions. These questions are very important for completion point of view. So moving to Faraday's second law. Faraday's second law, which suggests that when two or more different electrolytes are connected in series and same quantity of electricity is passed through them, then ratio of weights deposited, weights plural, is always in ratio of their equivalent weight. For example, W1 upon W2 will be equal to E1 upon E2. Class, let us solve a numerical here. Question is, copper sulfate and ZnSO4 are connected in series if during electrolysis 31.75 gram of copper was deposited, find the weight of Zn deposited during same time interval. So class, as per Faraday's second law, we can very well write W copper upon E copper. See, W1 upon E1 can be equal to W2 upon E2. So we can very well write W copper upon E copper equals to WZn upon EZn. And class, atomic mass Zn equals to 65 and copper equals to 63.5. So weight of copper has been given to us 31.75 upon 63.5 divided by 2. And this must be equal to weight of Zn. We are supposed to find out equivalent weight of Zn 65 by 2. So 2 will get cancelled with 2. And if you solve it, it gives you 2. 65 comes here. So weight of Zn equals to 32.5 grams. So class, in this way we can will solve numericals on second law of electrolysis. That is Faraday's second law of electrolysis. Class, with this Faraday's second law of electrolysis, we have completed our first topic, that is electrolysis. Now we will move to our second topic, that is called electrolytic conductance.